Hello and welcome to Lecture 60 of my course From Data to Decisions. I'm Chris Mack, your instructor, and in this particular lecture we are going to look at generalized linear modeling in R. To do generalized linear modeling, we'll use a function called GLM, an extension of the linear modeling function we've been using for a long time. So to start, let's pick some data. Tribe data that I've used before when demonstrating ordinary least squares regression. I will set up just a specific set of 11 numbers and plot them up for you. All right, so here's a graph of those numbers, and you can see that they're kind of randomly spread around a linear trend. We've actually seen this data before. It's part of the Anscombe problem sets or data sets that we've used to demonstrate some issues related to ordinary least squares regression. You know how to model this in R using OLS? Just use the LM function, linear model. Y is a function of X in this case because there's only one predictor variable. And we run the model and I print the summary. The summary shows me that the intercept is 3, the slope is 0.5. Both of those parameters are significant from a t-test perspective. Now, what we'd like to do now, this is all review. You've seen all that a bunch of times. If you've used R for any linear modeling, you know exactly what's going on. But let's look at a new routine called generalized linear modeling. This is what we talked about in our previous lecture. And in generalized linear modeling, we can specify one of a number of link functions and one of a number of probability distributions to describe the distribution of the residuals. Those distributions have some constraints. They have to be from the exponential family of distributions, but there's a lot that properly falls into that category. Now, what kind of link functions, what kind of probability distributions are available? Well, here you actually specify the family, the distribution family first, and then the link function to go with it. Here are a number of family distributions that are possibilities. We're going to see that the binomial family is the one that we'll use a lot with the logistic regression. But we can have a good old Gaussian or normal distribution, gamma distribution, Poisson distribution, and others. For each distribution family, there is a specific default link function. So if you don't specify the link function, it reverts to this default. And it's a kind of a natural link function to use with that distribution, but it's not the only link function that you can specify. The Gaussian distribution is what we assume for an ordinary least squares regression. And guess what? The link function is the identity function. So if we use generalized linear modeling with a Gaussian family and the identity link, well, are doing exactly ordinary least squares regression. So let's do that and using the GLM function rather than the LM function. We specify family equals Gaussian and link equals identity. We will run that model and give us the summary. Let's look at the summary. We'll look at that. Intercept of 3 and a slope of 0.5. Standard errors are identical to what they were before. Let's double check one. Standard error of the slope, 0.1179. Let's go up to our OLS. There it is, 0.1179. All right, so the generalized linear modeling routine finds the maximum likelihood estimator. And maximum likelihood estimator for a Gaussian distribution of residuals and an identity link function is nothing more than ordinary least squares regression. That's a little bit about the mechanics, but of course we have no reason to use the GLM function if we're going to use a Gaussian family of distribution and identity link. However, let's pick a different data set and just try out a different kind of regression, in particular a logistic regression. And the data set we're going to use is survival on the ship, the Titanic. Everyone knows about the Titanic. It sank in, what was it, the 20s, and a large percentage of the people died. Something like 38% of the passengers survived. Everyone else died. It was a very tragic accident. And a lot of people have studied this tragedy to try to understand what impacted survival. And this data set is in a package, which I've already installed, but you will need to install, called Titanic. Once you install that package, you load the library up, and it has data that we can try to understand. I'm going to use this data set called Titanic Train. This is training data. It also has some testing data that you can compare to. We'll just look at the training data, and I'll stick all that data into a variable called data.raw. All right, let's look at that data.raw. The first column is called passenger ID, and it's nothing more than the passenger ID. We're not going to need that. Survived is an indicator variable, 0, 1. 1 means that that person survived, and 0 means it doesn't. Every row is a different person. In fact, this fourth column over here is the name of the person. We're not going to, of course, need the names. We're going to need some of these other variables. P class is the passenger class, first class, second class, and third class. Sex is the male or female. Age of the passenger. Notice that here's an NA value. NA, it means not available. That person's age isn't available. We don't know what it is, so we mark it in a specific way called NA. SIB SP is how many siblings or spouses of yours were on that same ship at the same time. So siblings and spouses are all people of the same generation who are related to you. That's this column. So you see some people have 0, some people have 3, etc. P arc is a parent or child. Parent or child. So do you have your parents on the same ship or your children on the same ship? And if so, how many, right? So 0, 1, 2, etc. Ticket is an identifier for the ticket number. We're not going to need that at all. Fare, how much they paid for the ticket. Cabin, what cabin were they in? That might be useful if we had some map of where all the cabins were, but we don't. We're not going to use that. And then embarked is which city did you embark from? Q is Queenstown, and S, I think, is Southampton, and C is Chelsea. I can't remember exactly. But we have these 3 different cities in which they joined the boat. And that's the data in our Titanic data set. The question is, can we develop a model to predict probability of survival based on what passenger class you were, whether you're male or female, how old you are, whether you had siblings or spouses on the boat, etc., etc. Now, here's one of the problems. Some of the data has blanks in it. Look at the cabin here. We find that some of them are marked with NAs. Other of these cells are not marked with NAs. They're just blank. We're going to want to make sure that every blank cell is marked in the way that R can recognize, and that's the NA marking. R has lots of routines to understand what to do or options with what to do with NA, but blank is just another data point as far as R is concerned. So let's first clean up our data. And this is, well, a more general lesson for modeling. The first thing you have to do is look at your data, and probably you have to clean it up. It's rare that you're going to get a data set that is absolutely perfect, exactly in the right shape for you to use it to generate models. And here's one of the examples. So we're going to use this command to apply the R variable NA or the R data value NA in place of a blank. So what we'll do is we'll use this data.raw equal blank. So what that's going to do is it's going to look through every single cell, and every time it finds a cell where data.raw is identical to blank, then this little command here will be true. This is a logical equals, and it's asking, is data.raw logically equal to blank? Whenever that's true, then it will execute this command, which is take an A and stick it in that particular cell. As soon as I run this, now I go look back and look at my raw data. You see that every place that was a blank here in the cabin is now marked with an NA. We don't have any blanks left in our data. We only have not availables, NAs, wherever there's no data available. Now, to further our cleanup, let's try to find out how many not available data points we have. To do that, we can do it in a couple of ways. The first way we'll do it is this sapply. Sapply applies a function to the data. So I'll take the data.raw, then I'm going to do a function of x. That is, it's a function of columns. And I'm going to sum is.na x. So is.na is asking the question, is it an NA, a not available? So it'll look through every single data point and ask, is this data point not available? If it is, then is.na becomes true. Sum of that adds up all the truths. It counts the number of truths. So we can use sum as a way of counting when a particular condition inside the parentheses is true. So the function I'll apply is count the number of NAs, every column of X, over the entire data. So let's run that and see what we get. All right, well, let's look at what we got. We have all the columns, and underneath every column, it tells me how many NAs it found. So passenger ID, 0, survived, 0, P-class, 0, name, 0, sex, 0, age, 77. Now, I'll look at the next column here to show that there are 891 data points. That's the length of one of the columns. So 177 of those 891 passengers we don't have age information for. Well, that's going to be important because if we want to use age as a variable in our regression model, then we're basically going to throw away 177 passengers from the data set. And that's a choice we're going to have to decide whether we're willing to make. You see the cabin, there's 687 NAs. We don't have a whole lot of information about the cabins. We're definitely going to ignore cabin. Over here, embarked, we had 2 passengers where we don't know where they embarked. We could probably live with that. There's now a choice for us, taking advantage of what we've just seen, to decide which of the columns we want to use. So I'm going to create a new data. Let me call it just plain old data, as a subset of the original. So I use this command subset. It takes the original data, data.raw. It's not original anymore. I've actually modified it by changing all the blanks to NAs. But then I'm going to select specific rows. I'm going to select the 2nd, 3rd, 5th, 6th, 7th, 8th, 10th, and 12th row. Those are all the rows that I care about. You can go and look at the data and see that means I'm getting rid of the passenger ID, the name. I'm going to get rid of the ticket and the cabin. Those are all things that I know I'm not going to need at all to do my modeling work. So let me get rid of them. And if I go look at the data that results, you see I have everything but those things I threw away. Now let's do a linear modeling. What kind of modeling should we do? Well, our output is a binary data. Either you survived a 0, 1, or you didn't survive 0. That means we're trying to predict the probability of survival. when we're trying to model a probability, one of the most popular ways of doing that is with a logistic regression, as we've already talked about in our class. So let's use GLM to do a logistic regression. To do that, set the family to be binomial. Binomial is the probability distribution of a binary variable, zeros or ones, and logit is the length function for a logistic regression. So suppose we wanted to look at the impact of sex, male or female, on your probability of surviving. Okay, well, let's run that model. Model is done. Let's look at a summary of my model. You see, I have an intercept. And then, well, hold on a second. Sex is a categorical variable. It's either male or female. How do we do a regression on that? Well, we need to convert our categorical variable into an index. And R will do that for you automatically. If you give GLM a column of data that has categories like male and female, it will automatically convert those categories into the proper number of indicator variables. In this case, I only have two different possibilities. You want to make sure, use a command called level. So if I do levels of data.raw $sex, and I asked how many levels there are, it doesn't like that because this is not a factor. So I have to first convert it to a factor. All right, well, what's the difference there? As it is set up here, these are character strings. You can't really tell from looking at it, but it just turns out that this is a character string called male. This is a character string called female. And again, when I give that to R, it will automatically convert it into factors, which are male and female. So if I use this factor command, it converts that text string, character strings, male and female, into factors, male and female, and then it counts the number of levels. And there it is. Now that I've converted it to a factor, I can count the levels, and it says there's two levels. One's called female, the other is called well, that's pretty obvious when it comes to sex, but for other things like, say, embarked, it may not be so obvious. How many levels of embarked are there? Well, we can ask and see that, oh, there's C, Q, and S. There's 3 levels for the variable embarked. All right, so when we do the modeling, it automatically converts male and female into a indicator variable. It gives the name sex male. The reason is when it went down that column of sex, the first variable it came to was male, so it just arbitrarily assigned male to be 1 and female then to be 0. Then it takes that variable, that indicator variable called sex male, and it found the best fit coefficient or slope to be minus 2.5. Let's interpret what that means. What does that mean? Remember, this is a logistic regression, so the y predictor variable, the response variable that we're predicting here is pi over 1 minus pi, the log of that. So the log of the probability of survival divided by the probability of failure, of dying on the Titanic. So the probability of survival divided by the probability of dying is called the odds of surviving. And so the output of a logistic regression is the log odds. This coefficient of sex male is minus 2.5. That means the log odds is decreased by minus 2.5 if you're a man compared to if you're a woman. In other words, you had a lower survival probability if you were a man compared to a woman. If you wanted to convert that to just the odds, I'd take the exponential of that value. So for example, I could do EXP of model dollar coefficients, and it will exponentiate both of these coefficients, the intercept and the sex male. And now the odds are 0.08 smaller for a male, factor of 0.08 smaller for a male versus a female. This is what we call the odds ratio. Ratio of the odds for a man compared to the odds for a woman. And it's, like a factor of 12 smaller for a male compared to a female. That's the kind of things we can do with logistic regression, and that's the kind of things we can do with generalized linear modeling. In our next lecture, we're going to dive into logistic regression a lot more, and in fact, dive into the Titanic data set in a lot more detail to see some other interesting aspects of doing logistic regression. Till then.